Before we begin this module, let's take a moment to think about a very common type of prediction problem in the real world. Many decisions in business, science, engineering, and technology involve predicting numerical values. For example, we might want to estimate how much a house will sell for, forecast next month's revenue, or predict how much energy a city might consume tomorrow. These kinds of questions involve continuous outcomes rather than categories. In earlier modules, we discussed neural networks as systems that learn patterns from data. In this module, we extend that idea further by exploring how deep neural networks can be used to predict continuous numerical outcomes. You will build on your prior understanding of regression and see how neural networks extend traditional regression approaches by learning more complex relationships in data. We will also discuss some important challenges that arise when models become deeper and more powerful, and we will examine how these models are evaluated to ensure that their predictions remain reliable when applied to new data. By the end of this module, you will have a deeper understanding of how neural networks can be used for continuous prediction tasks in real-world applications. Before we dive deeper into the concepts in this module, it helps to briefly look at the roadmap of what we will explore. In this module, we begin by connecting continuous prediction problems to the regression concepts you have already studied. This will help reinforce the idea that many neural network applications are extensions of familiar statistical learning methods. Next, we will examine how neural networks are able to generate continuous outputs, allowing them to make predictions about quantities such as prices, measurements, or forecasts. We will then discuss the role of hidden layers and why deeper neural networks can capture more complex relationships in data. After that, we will compare situations where a simple regression model may already be sufficient with situations where a deeper neural network can provide additional benefits. We will also examine some of the risks that come with using deeper models, including the possibility of overfitting. And we will briefly introduce strategies that help manage these risks. Finally, we will discuss how model evaluation works in the context of regression neural networks, including how training and testing performance help us determine whether a model is truly learning useful patterns. By the end of this module, you should have a clearer understanding of when deep neural networks are appropriate for predicting continuous outcomes and how their performance can be evaluated. To understand how neural networks can be used for regression, we first need to revisit the idea of continuous prediction problems. In many real-world situations, the goal is not to assign a category or label. Instead, the goal is to predict a numerical value. For example, an analyst might want to predict the price of a house based on factors such as its size, location, and age. A business might want to forecast future sales revenue, while an energy company might try to estimate how much electricity a city will consume on a given day. In healthcare, models may even be used to estimate measurements such as blood pressure or glucose levels. All of these examples share one important characteristic. The outcome we are trying to predict is a continuous number rather than a category. Problems of this type are known as regression problems. In regression, the goal is to learn a function that maps input features to a continuous outcome variable. Traditional regression models attempt to learn this relationship using relatively simple mathematical functions. Deep neural networks extend this idea by learning far more flexible functions, allowing them to capture complex relationships between inputs and outputs. Because of this flexibility, neural networks can often model patterns that would be difficult or impossible for simpler regression models to represent. Now that we understand what regression problems are, the next question is how neural networks can be used to solve them. A neural network designed for regression still follows the same overall structure that we studied earlier. Information flows from the input layer through one or more hidden layers and finally reaches the output layer. The key difference appears in the output layer itself. In classification tasks, The output layer typically produces probabilities that correspond to different categories. In regression tasks, however, the network is designed to produce a continuous numerical value. In other words, instead of predicting a class label, the network directly predicts a number. For example, a regression neural network might estimate the price of a house, forecast next month's demand for a product, or predict the amount of energy that will be consumed during a particular time period. Because neural networks can learn complex mathematical relationships, they can approximate the function that connects the input features to the numerical outcome we want to predict. This ability to approximate complex functions is what makes neural networks a powerful tool for regression problems involving real-world data. Now let's take a closer look at why hidden layers are so important in neural networks. In traditional regression models, the relationship between inputs and outputs is often assumed to follow a relatively simple mathematical structure. For example, linear regression assumes that the relationship between variables can be represented by a straight line. However, real-world data rarely behaves in such a simple way. Many relationships between variables are nonlinear, and multiple variables often interact with one another in complex ways. This is where hidden layers become valuable. Each hidden layer in a neural network transforms the input data into a new representation. As the data moves through successive layers, the network gradually learns features and patterns that make the final prediction more accurate. Through this layered process, neural networks are able to capture nonlinear relationships, interactions between features, and complex transformations of the original inputs. As we add more hidden layers, the network gains the ability to represent increasingly complex patterns in the data. This is one of the main reasons why deeper neural networks can sometimes achieve better performance than simpler models when dealing with complicated prediction problems. At this point, it is important to recognize that deep neural networks are not always necessary. In many situations, a simple regression model can perform extremely well. When the relationship between variables is mostly linear, or when the dataset is relatively small, a traditional regression approach may already provide accurate and reliable predictions. Another important factor to consider is interpretability. Simple regression models are often easier to understand and explain, which can be valuable in fields where transparency and accountability are important. For example, analysts and decision makers may want to clearly see how each variable influences the prediction. In these cases, a simpler model may actually be preferable. Deep neural networks become more useful when the prediction problem involves complex relationships, large datasets, or many interacting variables. In these situations, the additional flexibility of deeper models allows them to capture patterns that simpler approaches might miss. The key idea is that model choice should depend on the nature of the problem and the data, rather than assuming that a more complex model will always produce better results. As neural networks become deeper and more flexible, they also introduce certain risks. One of the most important of these risks is known as overfitting. Overfitting occurs when a model learns the training data too well. Instead of capturing the general patterns that exist in the data, the model begins to memorize the specific details and noise present in the training dataset. When this happens, the model may produce very accurate predictions on the data it has already seen. However, when it's applied to new data, its performance can drop significantly. This happens because the model has learned patterns that are unique to the training data, rather than patterns that generalize to new situations. Deep neural networks are particularly susceptible to overfitting because they have a large number of parameters and a high capacity to represent complex functions. For this reason, when building deep learning models, it's important to carefully monitor how the model behaves and ensure that it is learning meaningful patterns rather than memorizing the training data. Because the deep neural networks have a large capacity to learn complex patterns, it is important to apply strategies that help prevent overfitting. One common approach is to increase the amount of training data. When a model is trained on a larger and more diverse dataset, it becomes more likely to learn the true underlying patterns, rather than memorizing specific examples. Another strategy involves the use of regularization techniques, which introduce constraints that discourage the model from becoming overly complex. We can also control overfitting by carefully managing the structure of the neural network itself. Limiting the number of layers or neurons can sometimes help prevent the model from becoming unnecessarily complicated. A commonly used technique in deep learning is early stopping. During training, the model is evaluated on a separate validation dataset, and training is stopped when performance on that validation data begins to decline. These strategies help ensure that the model focuses on learning patterns that generalize well to new data, rather than memorizing the training examples. Once a neural network has been trained, the next step is to evaluate how well it performs. To do this, we typically examine the model's performance on two different types of data: training data and testing data. Training data is the dataset that the model uses during the learning process. By analyzing performance on this data, we can see how well the model has learned the patterns that exist within the dataset. However, evaluating performance on the training data alone is not sufficient. A model may perform very well on the data it has already seen, but still fail to make accurate predictions on new examples. For this reason, we also evaluate the model using testing data, which consists of data the model did not encounter during training. Testing performance provides a more realistic indication of how the model will behave when applied to new, unseen data in real-world situations. By comparing training and testing performance, we can begin to understand whether the model is learning meaningful patterns or whether it may be suffering from issues such as overfitting. To interpret the results of a regression neural network, it is important to compare how the model performs on the training data and the testing data. Ideally, a well-trained model should perform well on both data sets. When the model has successfully learned the underlying patterns in the data, its performance on the testing data should be similar to its performance on the training data. However, if the model performs extremely well on the training data but much worse on the testing data, this is often a sign of overfitting. In that situation, the model has memorized the training examples rather than learning patterns that generalize to new data. On the other hand, if the model performs poorly on both the training and testing datasets, the model may be too simple or may not have been trained long enough to capture the relevant relationships in the data. By carefully comparing training and testing performance, we can better understand how well a neural network is learning and whether its predictions are likely to remain reliable when applied to new situations. Alright, let's start by setting up our notebook environment the right way. In the first cell, we import everything we'll need for the full workflow: loading data, preparing it, building a regression model with a deep neural network, and evaluating performance. We begin with NumPy and Pandas. NumPy is our foundation for numerical computation, and Pandas is what we'll use to load and manage the dataset in a data frame, which makes cleaning and exploration much easier. Next, we import Matplotlib so we can visualize results later, things like distributions, trends, and performance plots. Then we bring in several tools from scikit-learn. We import train tests split because we need to separate our dataset into training and testing sets. That way we can train the model on one portion of the data and evaluate how well it generalizes on data it has never seen before. We also import standard scalar. because scaling is extremely important for neural networks. If one feature has values in the thousands and another feature has values between 0 and 1, the model can struggle to learn effectively. Scaling puts everything on a comparable range, so training is more stable and efficient. We also import a few evaluation metrics that are standard for regression problems: mean absolute error, mean squared error, and R-squared. These will help us measure how close our predictions are to the actual continuous outcomes. You'll notice we also import several tools from stats models. Even though our main model is a deep neural network, stats models gives us extra diagnostic tools that are useful for regression style analysis. Things like checking for heterozygosity or multicollinearity. Those checks can still help us understand the quality of the dataset and the relationship between variables before we model. After that, we import TensorFlow and Keras, which is the deep learning framework we'll use to build and train our neural network. Then we do something very important. We set random seeds for both NumPy and TensorFlow. This is for reproducibility. In machine learning, randomness shows up in things like initialization and training behavior. So setting seeds helps ensure that if we rerun the notebook, our results stay consistent. And finally, we print the TensorFlow version so we can confirm the environment we're using, especially helpful if we're running this in Colab or switching between machines. Now, once our environment is set up, we move into the second cell, where we load the dataset. Since this notebook is designed for Google Colab, we use Colab's upload utility. When we run this cell, Colab will prompt us to select a file from our computer and upload it into the session. This code assumes the uploaded file is named housing.csv. Once the file is uploaded, we read it into pandas and store it in a data frame called df. Right after loading the data, we do two quick sanity checks. First, we print the shape of the data frame, which tells us how many rows and columns we're working with. That's a simple but critical step because it confirms the dataset loaded correctly and gives us a quick sense of its size. Then we display df.head, which shows the first few rows of the dataset. This lets us confirm that the columns look correct, the values appear reasonable, and nothing is misformatted before we move on to cleaning, scaling, splitting the data, and building our regression neural network. Now that the dataset has been loaded into our data frame, the next step is to perform some basic data checks and exploratory analysis. Before building any machine learning model, it's important to understand the structure and quality of the data we are working with. In the first part of this section, we run several quick validation checks. The command df.info gives us a summary of the dataset, including the column names, the data types of each column, and the number of non-null values. This helps confirm that the dataset was read correctly and allows us to quickly identify any columns that may contain missing data. Next, we explicitly count the number of missing values in each column using df.is_n, a open parenthesis, close parenthesis, .sum, open parenthesis, close parenthesis. Missing values can cause problems for many machine learning models. So, identifying them early helps us decide whether we need to clean or impute the data. We also check for duplicate rows using df. Duplicated parents, .sum parents. Duplicate records can sometimes appear in real-world datasets, and removing them helps ensure that the model is not biased by repeated observations. After these checks, we use df.describe to generate basic descriptive statistics. This summary provides useful information such as the mean, standard deviation, minimum values, maximum values, and percentiles for each numerical variable. These statistics help us quickly understand the general scale and distribution of the features in the dataset. Once we have validated the dataset, we move into the exploratory data analysis stage, often called EDA. First, we examine the distributions of the variables using histograms. We create a list of all columns in the dataset and then plot histograms for each one. Histograms allow us to see how values are distributed, whether they appear roughly normal, skewed, or concentrated in certain ranges. Understanding these distributions is helpful because extreme skewness or unusual patterns may influence how well a regression model performs. Next, we create box plots for each variable. Box plots are particularly useful for quickly identifying potential outliers. Outliers are observations that fall far outside the typical range of the data. While some outliers may represent valid observations, others may be data entry errors or unusual cases that can disproportionately influence model training. By scanning the box plots, we can quickly see whether any variables contain extreme values that may require further investigation. Finally, we perform another important exploratory step by examining the relationship between each feature and the target variable. In this dataset, the target variable we want to predict is price. We create a list of all the other columns and treat them as input features. Then, for each feature, we generate a scatter plot comparing that feature with the target variable. Scatter plots are extremely useful for regression problems because they allow us to visually inspect whether a relationship exists between the predictor and the outcome. If we see a clear upward or downward trend, that suggests the variable may be a strong predictor of the target. On the other hand, if the points appear randomly scattered with no visible pattern, that feature may have a weaker relationship with the outcome. Together, these steps help us gain an initial understanding of the dataset before we move forward to feature scaling, train test splitting, and ultimately building the deep neural network regression model. Now that we have explored the basic distributions of the variables and examined how individual features relate to the target, we continue our exploratory analysis by looking at how the variables relate to each other. In cell 6, we compute a correlation matrix using the numeric variables in the dataset. A correlation matrix measures the strength and direction of the linear relationship between pairs of variables. The values typically range from -1 to +1. Values close to +1 indicate a strong positive relationship. Values close to -1 indicate a strong negative relationship. And values near 0 suggest little to no linear relationship. After computing the matrix, we visualize it using a heat map style plot. Each cell in the plot represents the correlation between two variables, allowing us to quickly scan the dataset for strong relationships. This step is especially useful for identifying multicollinearity, which occurs when two or more predictor variables are highly correlated with one another. When multicollinearity is present, it can make it harder to interpret regression models and may destabilize coefficient estimates. Even though our final model will be a neural network, it is still helpful to understand these relationships in the data. Next, in cell 7, we run a traditional ordinary least squares regression using the stats_models library. The goal here is not to build our final predictive model, but rather to examine several classical regression diagnostics. We begin by separating the input features from the target variable, which in this case is price. We then add a constant term to the feature matrix, which allows the regression model to include an intercept. After that, we fit an OLS regression model using the stats_models implementation. Finally, we print the regression summary. This summary provides a large amount of information, including coefficient estimates, statistical significance tests, goodness of fit measures, and diagnostic indicators. These diagnostics help us understand how the variables behave from a traditional regression perspective before we move on to deep learning. In Cell 8, we take the diagnostic analysis one step further by examining the residuals of the regression model. Residuals represent the difference between the actual observed values and the values predicted by the model. In other words, they show us the prediction errors. First, we compute the predicted values from the regression model and then calculate the residuals by subtracting those predictions from the true target values. We then create a scatter plot of residuals versus fitted values. This plot helps us visually inspect two important regression assumptions: linearity and homoscedasticity. Ideally, the residuals should appear randomly scattered around zero with no clear pattern. If we observe curved patterns or systematic structures, that may suggest the relationship between variables is not purely linear. Finally, we plot a histogram of the residuals. This visualization helps us assess whether the residuals are roughly symmetric and centered around zero, which can be a signal that the model errors follow a reasonable distribution. Together, these tests provide valuable insight into the structure and behavior of the data before we move on to building the neural network model for regression. Continuing our diagnostic analysis, the next step is to more carefully examine the distribution of the model's residuals. In Cell 9, we generate what is known as a QQ plot, which stands for quantile-quantile plot. This visualization compares the distribution of our residuals to the theoretical distribution of a normal distribution. If the residuals follow a roughly normal pattern, the points in the plot should fall close to the diagonal reference line. Small deviations are usually acceptable, but large systematic departures from the line can indicate that the residuals are not normally distributed. While strict normality is not always required for prediction-focused models, this check gives us additional insight into the structure of the model errors. Next, in Cell 10, we perform the Bruch-Pagan test, which is used to examine homoscedasticity or constant variance of the residuals. The null hypothesis of this test assumes that the variance of the residual is constant across different levels of the predictors. If the test returns a small p-value, that suggests the presence of heteroscedasticity, meaning the spread of the errors changes across the range of predicted values. Identifying heteroscedasticity can be useful when evaluating the assumptions of traditional regression models and understanding the stability of prediction errors. In Cell 11, we move on to evaluating multicollinearity among the predictor variables using the variance inflation factor, or VIF. Multicollinearity occurs when two or more input variables are highly correlated with one another. When this happens, it can make it difficult to interpret the contribution of individual predictors in a regression model. To compute VIF values, we first add a constant column to the feature matrix and then calculate the variance inflation factor for each variable. The resulting table lists each feature alongside its corresponding VIF value. As a general rule of thumb, values above about 10 are often considered high and may indicate problematic multicollinearity. Even though deep neural networks are less sensitive to multicollinearity than linear models, it is still valuable to understand how strongly our predictors relate to each other. Finally, in Cell 12, we begin preparing the dataset for training a deep neural network regression model. First, we separate the input features from the target variable. The feature matrix becomes X, and the target values, which represent price, become Y. We also convert the target variable to a floating point format to ensure compatibility with TensorFlow. Next, we split the dataset into training and testing subsets using the train test split function. In this case, 20% of the data is reserved for testing, while the remaining 80% will be used for training the model. This separation is critical because it allows us to evaluate how well the model performs on data it has never seen before. After the split, we apply feature scaling using the standard scaler. Neural networks typically perform better when input variables are standardized, so that they have a mean near 0 and a standard deviation near 1. We fit the scaler on the training data and then apply the same transformation to the testing data to ensure consistency. Finally, we print the shapes of the scaled training and testing datasets. This step confirms that the pre-processing pipeline worked correctly and that the data is now ready for the next stage, which will involve building and training the deep neural network model. At this point, the dataset has been cleaned, explored, and properly prepared. Now we are ready to build and train our deep neural network regression model. In cell 13, we define the architecture of the neural network using Keras' sequential model. A sequential model simply means that data flows through the network layer by layer in a forward direction. We start by specifying the input layer, where the shape corresponds to the number of features in our scaled training dataset. This tells the network how many input variables it should expect. Next, we add two hidden layers. The first hidden layer contains 64 neurons and uses the ReLU activation function, which is commonly used in deep learning because it helps the network learn nonlinear relationships while keeping the training process efficient. The second hidden layer contains 32 neurons and also uses the ReLU activation function. Finally, we add the output layer. Because this is a regression problem, the output layer contains a single neuron with no activation function. This produces a continuous numerical prediction, which in this case represents the predicted value of the target variable. After defining the architecture, we compile the model. During compilation, we specify how the network should learn. We use the Atom optimizer with a learning rate of 0.001, which is a widely used optimization algorithm for training neural networks. We also define the loss function as mean squared error, which measures the average squared difference between predicted values and actual values. As an additional evaluation metric, we include mean absolute error, so we can track prediction accuracy during training. Finally, we print the model summary, which displays the structure of the network, including the number of layers and the number of parameters being learned. In cell 14, we begin training the neural network. Before starting the training process, we create an early stopping callback. Early stopping is an important technique used to prevent overfitting. It monitors the validation loss during training and stops the training process if the model stops improving for a specified number of epochs. In this case, we monitor the validation loss and allow the model 20 epochs to improve before stopping. The option to restore the best weights ensures that the final model corresponds to the best performing point during training. We then train the model using the scaled training data. 20% of the training data is reserved as validation data, so the model can be evaluated during the training process. We allow the model to train for up to 300 epochs with a batch size of 32 observations at a time. The early stopping callback will automatically stop training if further improvement is no longer occurring. As the model trains, the training history records how the loss and evaluation metrics change over time. In cell 15, we visualize these results using training curves. The first plot shows the training loss and validation loss across epochs. These curves help us see how the model improves during training and whether overfitting begins to occur. Ideally, both curves should decrease and eventually stabilize. The second plot shows the training and validation, mean absolute error, across epochs. This gives us another perspective on model performance by showing how the average prediction error evolves during the learning process. Together, these visualizations help us understand how the neural network learns over time and whether the model is converging to a stable solution before we move on to evaluating its final performance on the testing dataset. Now that the neural network has been trained and we have examined the learning curves, the next step is to evaluate how well the model performs on the testing dataset, which represents data the model has not seen before. In cell 16, we begin by generating predictions from the trained neural network. We use the model's predict function on the scaled testing features, which produces predicted values for the target variable. Because the output is returned as a column vector, we flatten the results so they are easier to work with when computing evaluation metrics. Next, we calculate several standard metrics used for regression evaluation. The first metric is mean absolute error, or MAE, which measures the average absolute difference between the predicted values and the true values. This gives us an intuitive measure of how far off our predictions are on average. The second metric we compute is root mean squared error, or RMSE. This metric is based on the squared differences between predictions and actual values, which means it penalizes larger errors more heavily. RMSE is often used because it emphasizes large prediction mistakes that may be particularly important in real-world applications. The third metric we calculate is R squared, which measures the proportion of variance in the target variable that is explained by the model. An R squared value closer to 1 indicates that the model explains a larger portion of the variability in the outcome. After computing these metrics, we print them so we can quickly assess the overall predictive performance of the neural network. In cell 17, we create an actual versus predicted plot. This visualization compares the true target values from the test set with the values predicted by the neural network. Each point on the scatter plot represents one observation. The horizontal axis shows the actual price, and the vertical axis shows the predicted price. Ideally, the points should fall close to the diagonal reference line, which represents perfect predictions where the predicted value exactly matches the true value. The closer the points cluster around that diagonal line, the better the model is performing. Finally, in cell 18, we examine the residuals of the neural network model. Residuals represent the difference between the actual values and the predicted values, which essentially captures the model's prediction error for each observation. First, we create a scatter plot of residuals versus predicted values. This plot helps us determine whether the prediction errors are randomly distributed or whether there are systematic patterns in the errors. Ideally, the residuals should be scattered randomly around zero without forming clear shapes or trends. Next, we visualize the distribution of the residuals using a histogram. This allows us to see whether the errors are roughly centered around zero and whether they follow a relatively symmetric distribution. Together, these evaluation steps provide a clear picture of how well the deep neural network performs on unseen data and help us assess whether the model's predictions are reliable for continuous outcome prediction tasks.